So for ionization energy, okay, this is going to be the trend of ionization energy across period 3. So you can see the graph that I've drawn over here. So you have sodium, okay, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. So the ionization energy, okay, is going to be generally, yeah, if you look at the general trend, okay, if I draw, okay, this is going to go up. Okay, if I draw this, it's going to go up as well, and this is also something like going up. Okay, but you will notice, okay, you will notice that, okay, there is going to be some abnormalities over there, which is going to be when it comes to magnesium to aluminium, when it comes to phosphorus to sulfur. Okay, there is going to be some kind of a decrease, okay, than what we expected. But before that, okay, I think this is going to refresh your memory about ionization energy. What is ionization energy? Ionization energy is going to be the energy required. Okay, the definition is very, very important. We have done this before. Okay, it's the energy required to remove one electron, okay, from each atom in 1 mole of element, and that element must be in gaseous state, okay, to form 1 mole of gases plus 1 ions. And this is the definition of what? Not only the definition of ionization energy. This is very specific. This is first ionization energy. So do remember this graph that I'm drawing over here is actually the trend of first ionization energy. Okay, not simply because ionization energy is going to be successive. You can keep on removing one electron. Even after you remove, let's say from one electron from sodium, you get Na plus. From that Na plus, you can still remove another one more electron to give you Na2 plus. That is going to be second ionization energy. So this is going to be the definition for first ionization energy. And we have, okay, over here, there is going to be some sort of an abnormality, okay, which is going to be rather than increasing, okay, the reason why such ionization energy is supposed to increase is because I think it's based on what you have discussed earlier in your PowerPoint presentation, which is going to be when you go across period 3, we know the number of proton is increasing. So when the number of proton is increasing, generally your nuclear charge is increasing. So the ability to hold the electron shells closer to itself is going to be more. That's why your atomic radius becomes smaller across the periodic table, or across the period 3. And what happens now, okay, the same thing, if I want to remove one electron, it's going to be difficult to remove, okay, across the period 3, because the nucleus is going to hold the electrons closer. So I am going to end up spending more energy to remove the electrons. So that's why generally the trend will increase. But there is going to be abnormalities when it comes to from magnesium, okay, from magnesium to aluminium. So we need to look into that. And then from phosphorus to sulfur. So in order to do that, okay, we need to look at our electronic configuration. So if I write down the electronic configuration for magnesium, okay, this is going to be the electronic configuration for magnesium. So for aluminium, so I will write down as 1s2, 2s2, 2p6, 3s2, and 3p1. So it means that when you want to remove the electron from aluminium, you are removing it from 3p. And what is 3p? 3p, even though, okay, they are from the same principal quantum shell, okay, it's from 3, okay, but 3p is going to be slightly further from the nucleus. Okay, 3s is slightly nearer to the nucleus. Therefore, if I actually put it in terms of diagram, yeah, if imagine this is going to be the nucleus. So this one, imagine is 3s, okay. So if I have 3s, 3p is slightly further, okay. So if you want to hold the electrons in 3s, yeah, the nucleus will have better ability to hold the electrons. But when it comes to the electrons in 3p, the nucleus will not be able to hold them properly. So that makes it easier for the electrons to be removed from 3p. So the keyword that we are looking over here is, okay, 3p is slightly further from 3s. So less energy is required to remove the electron. So the keyword is related to distance. Okay, that is what we are looking for. Okay, and for this one, okay, for phosphorus and sulfur, okay, for phosphorus, this is going to be the electronic configuration. So if you look at for sulfur, the electronic configuration will be something like this. 3p4. So if I want to draw in form of boxes, okay, so the electrons will come over here, will come over here, will come over here. All the orbitals in 3p, okay, will be singly filled. Okay, they are singly filled. But when it comes to 3p4 over here for sulfur, the electrons 1, 2, 3, and then one of it, okay, one of the orbital is going to be paired. Okay, this paired electron, okay, will create what we call a spin pair repulsion. This spin pair repulsion is going to be great. So it will make the electrons, okay, the electrons that is over here, to be easily removed. Okay, to be easily removed, and the energy to remove that electron is going to be less. So that makes, okay, the keyword over here that we are going to talk over here is going to be the spin pair repulsion. Okay, so that is what we are going to look. So if you look at the graph over here, so the important thing to tell over here, this is going to be the distance. The important thing that you need to tell over here is going to be the spin pair repulsion. Okay, that is our today's lesson. Yeah.